Oh, here we go again, breaking things up into two parts. I know, you get tired of it. Just want to go faster, but I'm slowing you down. We're going to solve quadratic equations by graphing in this lesson. How can quadratic equations be used in computer simulations? A golf ball follows a path much like a parabola. Because of this property, quadratic functions can be used to simulate parts of a computer golf game. One of the x-intercepts of the quadratic function represents the location where the ball will hit the ground. Recall that a quadratic function has the standard form of f of x equals ax squared plus bx plus c. In a quadratic equation, the value of the related quadratic function is 0. So for the quadratic equation 0 equals x squared minus 2x minus 3, the related quadratic function is f of x equals x squared minus 2x minus 3. You've used factoring to solve equations like x squared minus 2x minus 3 equals 0. You can also use graphing to determine the solutions of equations like this. The solutions of a quadratic equation are called the roots of the equation. The roots of a quadratic equation can be found by finding the x-intercepts, or zeros, of the related quadratic function. Solve x squared minus 3x minus 10 equals 0 by graphing. It's nice to know where the axis of symmetry is to know where your table should be centered around. So if we use the x equals negative 2b over 2a formula, we're going to have negative a is 1 and b is negative 3. So negative 3 over 2 times 1. Negative times negative is a positive, so we're going to get 1.5. And if I plug that into my calculator, I get negative 12.25 for the y part. Okay, so they gave us a lovely vertex there. So that gives you an idea of what numbers you want in your table. You want it centered around 1.5 for the x. Okay, for time I went ahead and started filling in our table that you guys can get from your handy dandy table feature from your calculator, and then we can plot points. Conveniently, at negative 2, I'm exactly at 0, and as I am also at positive 5. Interesting how they left those numbers out of the table, isn't it? So where this equals 0 is at negative 2 when x is negative 2 or x is positive 5. And it's braces, not parentheses, because it's not an ordered pair. The ordered pairs are negative 2, 0 and 5, 0. Okay, first step to solve by graphing is we always want everything on one side of the equation. So we're going to add 9 to both sides. To find where our vertex is going to be, x equals negative b over 2a again, so negative 6 over 2 times 1 is going to be 3. So we have two numbers less than 3, two numbers more than 3. That's nice. Put in 1 for x, we'll get out 4 for y. 1, 0, 1, 4. See the symmetry? Isn't it nice? 4's the 1's the 0. And we can go on and on, up and down forever. Well, they gave away the mystery this time. Where will the equation equal 0? At 3. So this time we're only going to get one solution. And you probably already recognize that as a perfect square. First term's a perfect square, last term's a perfect square. Square root of 9 is 3, so if I have x minus 3 squared, check it out. First term squared, first time, second times 2, I get negative 6. Yep, it's a double root. Okay, this time when we go to find our axis of symmetry, negative 2 divided by 2 is going to be negative 1. So they have two numbers less than negative 1, two numbers more than negative 1. 9 minus 6 is 3 plus 3 is 6. That's not too tough even without a calculator. But it's sure fast with that table feature. And then we can plot our points. And if I'd given you time to think about it, you could see that these numbers are going to go up. Either way, the lowest I ever was, our minimum is at 2. So when will this equal 0? Never. So there are three things that can happen with a quadratic equation. Either it can cross twice, which happens a lot, just once when we have a double root, or not at all in situations like this. The roots of a quadratic equation are the x-intercepts of the related quadratic function.